Okay, welcome everyone. So first thing, getting a couple of questions on assignment 2, and you would think I would have clarified that by now because people ask this question all the time. But on the Fourier analysis, where I ask you to basically on the assignment, work with the temperature data signal and interpret things from the FFT. When it refers to Bruce's modeling exercise, that, and it's written here in the forum, that refers to I basically reproduced what was in the Bruce book for you, so you don't need the Bruce book, which is good. And so basically the modeling exercise is the idea that you could take the signal and fit a certain sinusoid to it and subtract, get the error, then fit another sinusoid of another frequency to the remaining error, subtract, and so forth. And by doing that kind of successive procedure, you can kind of extract what sinusoids are embedded in the data. Okay. And of course, the whole point of doing that was that we don't need to do that. We could do that, right? And get the same thing, but we don't need to do that because that's what the Fourier transform does for us. It basically will show us the significance of various sinusoidal cycles that are embedded in the data. Okay, so that's more or less what we're looking for there. Any questions on that? Okay. All right. And you can, read the forum post. Congratulations, Alex. You're the first person to ever use the forum. It was like I was paging down there and said, oh, there's something in the forum. That's never happened. Okay. But why not, right? Okay. So, well, first of all, assignment 1 graded. You should have gotten those back. I recorded a discussion of the solution, about 15 minutes or so, but of course you can fast forward through me to get to parts you want to. For the most part, there were no, real common misunderstandings or anything like that. I think for the most part, we get it. Does anyone have any questions from assignment 1 before we move forward? Okay, if not, and certainly you can drop those questions on me anytime, office hour tomorrow at 3, etc. Okay, so so we're still a little behind. We'll do a little catching up today. So where we left off, oops, go back, was, basically we finished our review. I'll say mostly review of probability and statistics. Some of it may not have been very familiar to you, but it's basically things that are usually covered in probability statistics course. And we kind of left off here with this discussion of covariance and evaluating the relationship between 2 random variables. And so we looked at a case where we basically took 2 signals in MATLAB and determined properties of their covariance by using the COV function. And I was pointing out that what you get from MATLAB's COV function is actually a covariance matrix of X with itself and Y with itself, and then the cross elements, so these are actually variances of the 2 random variables and the covariances on the off diagonal portion. And those two have to be identical, of course. And the idea, that I was kind of leaving you with was that this gives us a way of kind of assessing just how related two random things are. Okay. And you can look at that in a lot of different ways. One way is to say, okay, if I know X, how much information do I have about Y? Or if I know X, how well could I predict the value of Y? Right. And so that kind of expresses, how much randomness is shared between the two versus how much they kind of independently have. And again, that's a kind of a, the absolute number you get there doesn't necessarily mean anything because it depends on the signal that you have. So you really have to look at it in the context of the actual variances of the two. Okay. If this is a small number, and I don't have, I don't necessarily have a rule for you as to what a small number is, I'll say 5% or less, but that's not a, hard and fast rule. If this is a small number relative to these, then, then any relationship is pretty small, and you could probably get away with assuming that they're independent of each other, right? If these are 0, then they're truly independent. And if it's, and then from there, as that increases, if it gets to like 20%, you kind of have to say, well, we can't really assume they're independent. There is some relationship there. And a lot of statistical analysis of data relies on trying to find relationships between things, especially in medicine, right? You get some data, you would like to know that, some measure is maybe prognostic or diagnostic for some condition. And so you look for those statistical relationships between things. That's data science, I guess. Okay. So that's kind of where we left off, was this discussion of, what it means, what this jointness means, and this covariance and dependence between random variables, which is going to inform a lot of what we're going to talk about today. Okay, so this is truly new material, and I highly doubt that any of you have seen this stuff before. So there we go. It's about random processes. So we talked about random variables. Okay, and so an extension of that is the idea of the random process. And so what we mean by this really is it's just a collection of random variables that may or may not be related, but we're assuming that there is some relationship between them. And in our context, we're talking about signals, right? So the idea is that over time, let's say we have 512 time samples, so there are 512 points in this signal. Each point in that signal vector is a random variable. Okay. And so as a result, and so we can, we could say each individual one is a random variable, and that's that, right? But that kind of misses out on a lot of information that we could have about their relationships over time, right? We're putting all of these random variables in the context of a signal that was all measured kind of together, right? And so we might refer to f of n as a random process, okay? Now, the thing that makes it random is that every time we measure that signal, we're going to get a different thing, okay? If it was deterministic, we would get the same signal every time, right? But that's not the kind of signal that we're interested in right now. And so these are random signals. And if we, use some of the language from random variables, now a random sample of a random process is one time observing all of the random variables in the, I'll say, collection or set, okay? So in the signal example, right, each time you measure those 512 random variables that evolve in time, you have a random sample of the random process, right? And so I'm trying to use the language random sample different than time sample, right? That's a unit of time. That a random sample, especially of a random process, is the measurement of the random thing one time. So, you know, these all come from the same random process, but every time I measure them, you know, you can see that they're different. And if we measured them 100 more times, we would get 100 more examples from this random process, random sample. Okay, so that's the extension of, you know, observing a random variable. Now we're observing a random process each time. The thing, though, about as we get to random processes, now we have two different ways of computing our statistics. Okay. We can compute temporal statistics, and that is to take one sample and compute its statistics over time. So if I take this guy, for example, and compute the mean and the variance of that signal over time, which we did as an example at the end of the last class, then that is an example of computing the temporal statistics, the time statistics. In other words, taking averages with respect to time. But there's another way to do it that are called ensemble statistics, which is to compute averages across all of these random samples. Okay, and so ensemble might be is probably a new term that is used in random processes. And so by the ensemble, we mean all of the possible random samples we might get. In other words, a whole bunch of signals. Okay. So, you know, in saying that, I could measure the temporal statistics off of just one random sample, but the ensemble statistics, I have to measure by taking a bunch of these random samples of the signal. Okay. So I'll go into a little more depth on these in a second. So first, temporal statistics, right? So, you know, again, averaging over time. So this sample of the random process, it has a mean of 0.64, you know, right about there. And so, you know, if you were to kind of draw a line where you thought the mean was, it'd be around there. It has a variance of 10.8. And so that expresses, you know, how much it varies about the mean. So that tells us something about the behavior of the signal, right? We get an idea of kind of where its baseline is and what its range of variation is. So there's information there. Now, here's the thing, right? The temporal statistics I compute, and remember, any statistic you compute from data is an estimate, right? It's so if I have let's say a random process, it has some true mean and true variance that I don't know. And if I measure it and compute the mean and variance, I'm estimating those things, right? And so as a result, since these are random, these all come from the same random process. But if I compute the mean and variance from each of these, you'll see that they vary. Okay, and that's an element of the randomness, right? These are estimates, so they aren't necessarily accurate, right? But you know, I could average all of the means there and maybe take some more and average the means from other signals and probably converge toward whatever the true mean is eventually, right? And that's just like, you know, when you do an experiment in the lab, you maybe do the same experiment multiple times, or you take multiple measurements of the same thing in order to average them out, because you're basically trying to reduce the randomness, reduce the random error. Well, it's the same thing here. Okay. By averaging things together, we reduce the effect of the randomness, right? You know, what we get depends on which measurement we use, and you know how the randomness happened to occur in that particular measurement. Now, we're going to contrast that idea with the ensemble, which technically is the set of all the possible signals you could generate from a given random process. And so by taking measurements of the signal, we're sampling from the ensemble. And the same idea applies, right? If we take, the more and more of these that we take, we're going to get a better idea of the true behavior of this thing. But the question is, okay, how do we estimate its properties? Well, what we're going to do essentially is average each of those individual random variables over the ensemble. So instead of going across time here, we're going to take time 0 in every single example that we've measured and average all of those together and get a mean value for f at 0, and then same for f at 1 and 2 and all the way out, in this case, to 511. Right, this one goes from 0 to 511. Probably should have been 1 to 512. MATLAB, but whatever. And we can compute variances for all of those too. Okay, so the idea of doing that, let's just think about the mean for a second. If we do that, the ensemble mean is actually a signal. It's not a single number, as in the temporal mean, okay? Because we've got the average of the random signal at time 0 and the average of the random signal at time 1 and time 2, et cetera, okay? And so by taking these three and averaging them together in that way, I get a mean signal, which is probably not a very good estimate of the true mean of this signal, because I probably need a lot more examples, right, to get a really good handle on what is kind of underlying this thing. But that's the distinction, right? When we take ensemble statistics, we get signals because we have statistics for every time point now. Okay, and you could similarly compute a variance signal by taking the variance of each one, and the higher order statistics, although we will not do this, skew, which is 3rd order, kurtosis, which is 4th order, and I just bring that up because I like to say kurtosis. But all of those would be signals, because we would have the variance as a function of time and the skew as a function of time, et cetera. Okay. Any questions on that? Okay. All right. Now we could actually take a, once we have the ensemble mean, we could take a temporal average of that if we wanted to get a single number, if we were justified in doing that. We would get the same mean that we got the other way, but the variance is actually much lower. Because the variance being squared is not linear, right? The mean would be linear, but the variance would not be. So you get a different result if you do that. Let me kind of step out for a second and just illustrate a little bit in a slightly different way. There's my pad. What we mean by the difference between these things. So we could have, some random signal. And some number of random samples of the random signal. Okay, so these are okay, and this is time. Okay, and so kind of another way of looking at what we were doing is basically temporal statistics average across time. Okay, but we'll use green. But ensemble statistics average across, I'll say, random samples of the signal. So basically, those are the, we can look at it essentially as averaging two different ways. Okay. And so in the ensemble statistics, basically, we just take all of our random samples, line them up, and then compute averages this way to get something, a signal in time. But temporal statistics, we would just take everything and average them this way. Okay. Sometimes that's seeing it illustrated that way is helpful. Okay. Any questions at this point? Okay. All right. So as we've said, right, there's two ways to compute statistics, and they may not give you the same thing. Okay, so they aren't equivalent at all, and you can't assume that they are. The temporal statistics give us scalars, single numbers, right? But ensemble statistics give us signals, or in MATLAB, vectors or arrays. Okay. Now, here's an important term that ties all this together. So if the ensemble statistics do not vary in time, then we refer to that random process as stationary. Okay, or this is the property of stationarity of the random process. So that is to say, for example, that the ensemble statistics, if we averaged them and had enough random samples to get an average that we could be confident with, the signal that we get should be constant in time. So an ensemble mean should converge to a constant. The ensemble variance should converge to a constant value, right? Which is to say that at every time point, the mean is the same and the variance is the same, or more generally, at every time point, the random properties are the same. Okay. And, people in the random process world will talk about strict sense stationary, which is like everything, or wide sense stationary, which is about as far as we care, which is going to be the first and second order statistics, which is mean variance, covariance. Okay. And that's all we're going to care about. So, when we say stationary, we really only mean that or care about that to second order. And another way of thinking of this in the context of what we talked about previously is to say that its statistics or its random properties are shift invariant. Okay, it doesn't matter where in the signal we look, the random properties are going to be the same, and that's going to be important, right? It's going to turn out that we need the property of stationarity in order to be able to use the Fourier transform to analyze the properties of the random process. Just as we need shift invariance in a system to be able to use the Fourier transform. Okay, so that's a term we're going to hear a good bit. This one you won't ever hear again, so I'm not even going to talk about it. It's just a more specific version of stationarity, but we'll skip it. Okay, so now I think I have a poll. So basically, just observe 3 examples of this random process. And I did not put them all on the same Y scale, so you may want to pay attention to that. Would have been better if I did, but I didn't. Let's see, where can I get my, okay. And so the question is, with these 3 samples from the random process, does it appear to you to be stationary? Or another way of saying it is, do you see any evidence that suggests that it's not stationary? So we'll fire that up, see what we get. Okay, couple more. Ah. And it's in. And there's the results. So most of you voted that it appears to not be stationary. Does anyone want to give their reasoning on why you think it looks non-stationary?
I was looking at like the end behavior of each of the signals, and like two of them have the first and third one have similar, but the second one's different.
That's fair. They look, you know, the kind of, especially the end behavior looks a little different, right? Unfortunately, the thing is that randomness can fool you. So this one actually is stationary, but it's not a, you know, it is perfectly reasonable for one to think that it is not, because you would have to see a lot more examples and maybe even compute some averages, you know, to be sure. Somebody who said yes, stationary, give me your reasoning.
So I basically just looked at sort of like where the mean was for each of them. And I mean, the scales kind of threw me off at first, but like
Yeah.
they're all around 0. And then I looked at sort of the ranges for each of the signals as well. And all of them were like somewhat like -10 to 10-ish.
Yeah.
So I was like, the variance is probably somewhat similar. So
Yeah.
looks stationary.
I think, you know, that's a good way to look at it, because we're trying to decide, okay, you know, is the mean going to be kind of the same everywhere? Is the variance, or the, you know, the degree to which it varies about the mean, going to be the same everywhere? And yeah, now, you know, for the most part, we're just guessing here. This one is stationary, I know, because I made it. Okay, but you know, this is really not enough information to be able to tell very well. And you know, that's part of the point, right? Randomness, you know, by its very nature, is very hard to nail down without a lot of data. And that's, again, the foundation of data science, right? Anything we do in data science to try to come up with predictive models and things like that, well, we need a lot of data to be sure it's going to work, right? In order to really understand the randomness of the particular situation. Okay, I got another one for you. How about this one? Okay, so now apply what you've learned to this particular case. Does this appear stationary? Couple more. One more. There we go. Thank you. And we have mixed results again. So someone who said no, non-stationary this time. How about tell us your reasoning?
Well, it looks like all three of them kind of have a positive slope.
Right.
So the mean towards the end would be higher than the mean towards the beginning.
Right, and that's exactly what happens in this one. So this one is non-stationary because the mean actually increases with time. And you can think about, okay, what if we took all three of those signals and assuming, you know, we measured 100 more and they all behave that way, right? Then we took the mean of each one, then, you know, we'd be likely to see the mean kind of just drifting upwards. And so the mean is not constant in time, which makes it not non-stationary. Now the variance, it turns out, is constant in time, but that's fine if, you know, once we miss out on the mean, it's non-stationary no matter what the variance does. Okay. Okay, thank you. Yeah, so that's the idea, right? I mean, if we just think about, okay, what if we average those and more like them? Now, it is possible, although again, statistically unlikely, but possible, that this actually is stationary and we just happen to measure three where they all drift upward. And we measured the next three and they drift downward or don't drift at all. So that's possible, right? But again, that's not what happened because I made this random process, so I know what it does. But hopefully you get the idea on that. We could also have a random process where the mean was constant, right? Let's say we had one that kind of behaved like this, constant mean, but the variance changes with time. We get kind of these bursts of noise or something like that. And if that behavior, you know, was kind of embedded in all of the samples, then, you know, the interpretation would be, well, the variance depends on time because we get these kind of noisy bursts, as long as they all happen at the same time, right, in all of our examples. Any questions about that? So that would be you know, it might have a constant mean, but the variance would not be constant with time. Okay, any questions there? All right. So that's the idea of stationarity, right? Now, to prove stationarity in any of these, what we would want to do is generate a whole bunch of random samples, random signals from the random process, and do that ensemble averaging, right? And see if the mean and variance converge to constant values, as they would actually in this case, or not, as they would in this case, right? The mean would converge to actually just a straight line that goes upward. Okay. To make this, by the way, to make this random process, I created some noise and then just added the time drift to it. Okay. Okay. So, you know, to prove it, we would have to take a lot of random samples and, you know, in order to be sure. Now, you know, again, we can't really do this in MATLAB, but theoretically, the whole idea of random processes can also be extended to continuous time signals and continuous time random processes. Okay, it's just that instead of having 512 random variables, you know, there's actually just an infinite number of random variables in that continuous random process. Okay, if you can wrap your head around that, you know, you kind of get it. But of course, everything we're working with, especially in MATLAB, will be discrete. And so that's okay. Now, here are 4 different random processes, okay? And so I've taken 3 random samples from each of these 4 different random processes. And the question, so clearly you can kind of look at them and see that, at least in most cases, they're different. Process 4 might look to you a lot like process 1. Turns out it's not, but it's hard to tell the difference by looking. But certainly processes 1, 2, and 3 have different properties. How would you describe how they are different? Somebody?
I mean, I would just say like lower frequency, I guess.
Sure. You can think of them in terms of the rate of change, or that translates to frequency, right? So, this one changes less quickly or has lower frequency properties than this one, which changes less quickly, lower frequency properties maybe than this one. Yeah, I mean, that's the main observation. You can also, another way of saying that is the kind of relative size, in time, along the time axis, of the features here are larger than the size of the features here, which tend to be larger than the size of the features here. And again, that's another way, just another way of saying frequency or rate of change. Okay. So the interesting thing about them, the histograms from all 4 are the same. And the histogram is a temporal statistic, right? Remember, the histogram is an estimate of the probability density function. And so if you know the probability density function of a random variable, you know everything about it. So we're kind of estimating the everything about it element of these things as a temporal statistic. So histogram in time, like we did at the end of last time. But that's the thing, right? So histograms from all of these are similar, which goes to say, hey, the temporal statistics don't give us the whole picture about these random processes. And I made these random processes to be this way for this example. So I basically gave them all the same temporal properties, but they don't look the same. Okay. So the idea is, hey, you know what? The temporal statistics aren't giving us enough information. They give us some information about these things, but they don't give us the distinctive information that describes what makes these guys look different. And so, well, you might be seeing where we're going. It's probably going to be something about the ensemble statistics that's going to describe the differences between these things. And a clue to that basically is that, the temporal statistics have no concept of the order in which the samples occur. In other words, if I take this signal and randomly scramble all the different time samples, or just sort them like this, I would actually get the same temporal statistics because all the numbers are the same. They're just in a different order. Okay. So, this is just another idea that the temporal statistics, by averaging over time, are losing some important information. Okay. And this is time for our 2-minute break. And then we'll continue on and explain, okay, how do we deal with that? So right now it's 2-minute break. There we go. Okay, we're back. All right, so now I'm going over to the next set of slides, the ones that are actually associated with today on the calendar. Okay, and so basically we were here. And so the point, of course, is that the order is going to be important, right? Now, if you think about the fact that, when we talked about ensemble statistics, we considered every time sample in our signal to be a random variable, then the thing to think about here is that they may not be independent of each other. In other words, we're interested in the covariances of relationships between different time points in the signal. This is the thing that's going to make the difference here. So let's kind of step back and say, well, okay, we talked about ensemble statistics and how we could compute a mean, individual means and variances for every element of our signal. But the other thing we want to think about is the covariances between different time points. Now, if we could kind of set up a way of expressing the covariance of every random variable with every other one in the set, we could structure it like this. In other words, the covariance of time 0 with itself, which would be its variance, and time 1 and so forth. And so all the way down the diagonal, we have the variances of all of the individual elements. Okay. But in the off diagonals, we have the covariances, in this case, F0 with F1, F0 with F2, F0 with F3, all the way down to F0 with the last element in the signal, and so on, okay? And this actually is a thing we would call a covariance matrix, although we're not really going to be spending a lot, we're not doing linear algebra so much in this class. You can in this stuff, but we're not going to. So pointing out, right, the diagonal elements are variances, because this is the variance of F at 1. The matrix is symmetric, meaning that things on opposite sides of the diagonal are equal, right? Because it doesn't, it doesn't matter if it's F0 with F1 or F1 with F0, they should be the same. And so new terms, okay? That set of all covariances between time samples in the signal is called the autocovariance of the random process. In other words, it's the covariance of the signal with itself, auto, self, right? And so this matrix could be used to describe the autocovariance. We could also, not subtract off, remember, covariance, we subtract off the mean. If we don't subtract off the mean, we have the correlation. And so there's the equivalent term autocorrelation, where we don't subtract off the mean. Okay. And so we could also, similarly have an autocorrelation matrix. When we write those out, they can be written this way. And actually, let me annotate that a bit, right? And so that expected value of F sub m would be the mean, and then we just subtract from the mean and take the expected value of that. But we're talking about the autocovariance at, time point m and n, the autocovariance between the statistical relationship between those 2 points in time. Okay. And autocorrelation, again, is similar. It's just the product of the signal at those 2 time points. So going back to the idea of covariance, right? And how we express covariance. If it's highly positive, there's a tendency for both of them to be higher than their means, right? In other words, if I have a lot of covariance in the signal at one time point and another, and it's high positive covariance, then they will tend to be, when I measure this thing, if one is above its mean, the other one will tend to want to be above its mean. And if I take another measurement and the first is below its mean, then the second one will tend to want to be below its mean. Okay. In other words, they will tend to, move in terms of the randomness, they will tend to move together. If the covariance is negative, they will tend to be on opposite sides of their means every time I do a measurement, right? Again, it's a tendency, it's not 100%. And if their covariance is 0, then they're going to move independently of each other. And there's going to be very little, you won't be able to predict one from the other. Okay. And this is going to translate into properties of how fast things can change in a signal. So, what would you expect between a time point here at the beginning of this signal measurement and a time point at the end of the signal measurement? Well, a lot's happened in between those two. So you wouldn't expect much statistical relationship, right? Especially in looking at how randomly this behaves in that time interval. So you would expect that to be a, nearly zero or zero covariance. Now, it may not be, but for our purposes, in most random signals, that's going to be the case. On the other hand, we might expect some kind of relationship between two samples that are close together, okay, in time, depending on how fast the signal moves in that amount of time. Within two samples, maybe it hasn't moved very far, in which case we might expect to see some positive covariance in that interval. Okay, and so the key point here is that the second order ensemble statistics expressed by autocovariance or autocorrelation determine the different textures or the features that you see in these. Okay, so yeah, their temporal statistics were all the same. Their probability density functions were all the same, but they have different autocovariance properties, which gives them the different textures or features, and is going to translate into, yeah, how fast they can change or what kind of frequency content they have. Okay, so given that idea, we can kind of step back and say, oh, okay, look at this guy, because he's the easiest one to see here, right? Things don't change very fast. So the idea is probably what we're going to find is that there's a pretty strong relationship over a relatively long, we'll say relatively long amount of time, over which we have some positive covariance. But as we move from there to here, the time over which we have significant positive covariance, that time interval is less. And as we go to here, it's probably even less because things are changing really fast. Okay. So that's kind of the idea. Whoops, sorry. Going back to this autocovariance matrix, right? If we have a 512 sample signal, then this matrix is 512 by 512, but we only need the upper triangle to be unique, but that's still a lot of stuff, right? That's like, on the order of 512 times 256 plus a little extra. Okay, so that's a lot of information we would need to describe that. But this is where stationarity comes in, okay? This makes things much easier because the statistics are shift invariant. So for a stationary random process, the autocovariance and autocorrelation only depend on the shift or time difference. And let me circle that. Or a term we will use and that MATLAB uses when you compute this thing is the lag. Okay. So it doesn't matter the absolute time at which they occur. It only matters how far apart two things are. And so when we, kind of go back and look at the autocovariance and autocorrelation, by the way, these are just typical symbols used for these things. I get them, I used to get them confused all the time. And there's not really a good way to remember, whether C is covariance or correlation or R. It's just, you know, but I will always give you the equation that I mean, okay? Correlation has 2 R's, so, whoops. I mean, they both have 1 R, but correlation has 2 R's, so it must be the R, you know, things like that to remember. And you don't have to really remember because you'll always be able to look it up. So what we're saying is these only depend on the difference between M and N and not on specifically what M and N are. So CFF at, you know, between 0 and 3 is equal to CFF between 1 and 4 is equal to CFF between, you know, 403 and 406. And this is in this example, the lag is 3 time units. Okay. So we can describe these now in terms of, instead of describing them in terms of 2 variables, we only need to describe them in terms of 1 variable if the random process is stationary. Okay, and so we could now write these as, you know, where N is actually general, right? We're taking, well, I'll use this one because it's a little easier to see. We're taking the correlation between F at any time N and F at any time, you know, K time units away from N. Okay. It's also true that, you know, once we do this, CFF of minus K, the negative lag is the same because it doesn't matter whether you're moving forward or backward. So this should be a symmetric function. So now we're going to need a lot fewer values because if I go back to the matrix structure, the idea now is that, oh, you know what? Those are all the same because it's stationary, so all the variances are the same. These are all lag 1. So we go kind of lag 0, lag 1, they're all the same. Lag 2 are all going to be all the same. Going like that, et cetera, et cetera. Okay, until we get to, you know, this is basically lag of N minus 1. Okay, and so we really only need to specify the top row now because all of the other elements of the matrix follow from that. Okay, and so, you know, how many independent values do we need now? It's just N, length of signal. So that's a lot better, right? So now it's 512 instead of 512 times 256 plus a few. Okay. Okay, so now I'm going to tell you that these are all stationary random processes, which means that their covariance, autocovariance properties are also similar in time, which is why the, you know, the way it varies, the features and so forth tend to be similar. In images, we call this textures. You can actually see them as textures in the image. Okay. Okay. In MATLAB, there is a function called XCOV, which actually says cross covariance. And it basically will estimate the autocovariance of a signal with lags up to however many max lags you do. Okay, and so basically, And by the way, just in general, I'm giving you a brief summary of this, but do make use of the MATLAB help files when we refer to these functions, because the MATLAB help files are actually very useful, and they have a lot of good information in them explaining different options and what they do. So that's actually for cross covariance, but if you just give it one signal, it computes the auto covariance. We'll talk about cross covariance later. And so basically what if you then did something like plot lags comma C, it will give you a plot that will do something like going up to whatever you decided, if you wanted to go just plus or minus 10 in lags or whatever. And it will give you some plot that looks like that. And so this would be the okay. So now that's an estimate, right? Because it just basically estimates the auto covariance from one example of the signal. So it will have some randomness to it. And so what I've done here is I've actually done that. And so this is these are basically auto covariance estimates. By the way, it says autocorrelation. Which is equal because mean is 0. Because I made them that way. Okay, so we're not worrying about the difference there. Right, if I go back, let's say to here, and say, oh, okay, if the expected values are 0, then the autocovariance and autocorrelation are the same thing. Okay, and so that's what we have here. Now, these are all plotted on a lag scale plus or minus 20. So they're all on the same scale and zoomed in, with respect to these. These are up to 512, but here we're only showing, a portion of the time scale. But these are all on the same time scale. And so what you see is that, more or less what we tried to describe earlier in words is that in this case, there is a range, and it's actually beyond this plus or minus 20. There's a range where we have significant positive autocorrelation or autocovariance. And it's much wider than, say, this one, because this one it drops down to 0 within about 7 or so time points. Okay, and so the range over this one has positive covariance is, plus or minus 7 time points, whereas this one is beyond plus or minus 20. And this one drops almost immediately. In other words, there is almost no correlation between a time point and its neighbor. And this one's weird because we actually get negative cases here. Okay, so it's positive, then negative, then positive again, and we'll see what that does to the system later. But this is a case where we actually get significant negative covariance, which remember means things move oppositely. Okay, we'll see how that manifests later. Okay, so any questions on this? These are autocovariance estimates from these things, and they're clearly different, right? So even though the temporal statistics were the same, these are different. If we take a closer look, right, the other thing to observe is that, and it's a little easier to see here. So now I've scaled the time scale the same. So it's about a length of 40. So these are kind of appearing on the same time scale. And what you see is basically these random features resemble the autocovariance. In other words, we get blobs, you could say, or the size of features, size of things that look like the size of the autocovariance. This is process 3 on a much larger scale from plus or minus 100. And you see that now these are still random, right? But basically the size of these kind of random variations that we get are similar to that. Does that make sense? And if we go back to here, you know, this one is very narrow, almost looks like a delta function. There's a reason for that. And these are also going to tend to be very narrow. Okay. Now, but not always, right? Sometimes you get two that are close together, and that's going to happen because it's random. Process 4, harder to tell. So we'll see more about process 4 later. Process 4 is a little different from the others. Okay, so the key point there is that features in the autocovariance function resemble features generated by the random process. And this, by the way, is also true. When you apply this to images, you get random textures in images. The autocorrelation or autocovariance function, which is two-dimensional and an image in that case, you know, generates features that look like textures. And by the way, that's a way that they generate random or generate natural textures, is to figure out an appropriate autocovariance random process model to generate things like marble or wood grain or things like that. And you can even extend it to add colors to them. Basically, each of the 3 color channels become random, but there are also relationships between them. And so that's a way that, say, in video games and other computer graphics, they can kind of randomly generate natural textures by assigning a certain random process model to it. And it makes use of all the same math as we're using here. Okay, so to kind of sum that up, right? If we're talking about autocovariance and autocorrelation, and, you know, again, assuming stationarity, which is mostly what we're going to assume from now on, unless I ask you to determine if something is stationary or not. Now, okay, so these are conceptual, but also we can sit down and calculate them. Now, sure, we can rely on MATLAB to do that, but you should have some idea of how this gets calculated, okay? So if you were taking a mean, you would basically sum up everything and then divide by the number of examples that you had, right? So in this case, if we say, let's just say autocorrelation, well, if we wanted to estimate the autocorrelation, we would take every example that we have of a time point and a time point k time points later, take their products, sum them all up, and divide by the number of examples that I had, right? So, and this basically says the same thing. If I was computing expected value of x squared from a set of samples from a random variable x, right, I would just like take all of those, square them all, sum them, and divide by how many I had. Okay. So you can compute autocorrelation the same way, right? If you were computing the expected value at, so this would be autocorrelation at lag 1, right? if I was trying to estimate that, I would take all of the examples of the product of a time point and and the next time point, sum them and divide by the total. And I think it's easy to see, fairly easy to see this just by, I just did it in an Excel spreadsheet, right? So here's f of x. Here are all, here's basically f of x shifted by 1. So, this one goes to here, this one goes to here, and so forth. Then I take all those products across of f of x times f of x plus 1. I sum up all the examples that I have, and then to get the expected value, I divide by how many examples that I had. Okay, and this is exactly what MATLAB does when it computes these estimates. Okay. So, that's a pretty straightforward process. You can look at it graphically also and say, okay, if this is my original signal, then I take the signal and shift it by 1, multiply term by term, then sum this way and divide by how many I had. And so that gives me RFF of 1. Now, that gives me 1 point in the autocorrelation function, right? And so to get lag 2, I basically start here. I shift this by 2. Okay, what did I do? I shifted it that way. It doesn't matter which way I shift because I should get, well, no, I'll qualify that. It might matter which way I shift, but they're just two different estimates. And so I shift it by 2 and do the same procedure. But you'll notice I'll have one less example to work with when I shift it by 2. If I shift it by 5, I'm getting fewer and fewer, I'm getting fewer examples, right, of legitimate pairs. So what this means is as as lags increase, just as, when you have fewer examples of computing a mean, it's less accurate. As I get to more and more lags, my estimate is less accurate, right? Because I have fewer examples to work with. Okay, and so this basically says it in words. This was autocorrelation where we don't subtract the means. If we wanted autocovariance, we would just reposition the signal by subtracting its average value and follow the same procedure. So start with the signal with the mean subtracted, do the shifts, multiply, add, divide, kind of thing. Okay. And that is where we're going to leave off. So there's just a little bit more left. And so we're close to being caught up. So I'm glad for that. Does anybody have any questions? Okay. All right then. Thanks everybody. Good to see you again.
I just have a question.
Yeah, go ahead.
Do we get to work on the homeworks during the weekend?
Yes. Yes, you do. Yeah. So I know it's, like I said, I know it says Friday, and I'm going to leave it that way because I'd like to encourage you to get it done on Friday. Then you don't have to work on it on the weekend. But as long as you have it to me by Monday morning, I will be fine with that. Okay.
All right. Have a good weekend.
All right.
Thank you.
I'll see at least some of you tomorrow at 3. Okay.
Thank you.
Thanks, everybody.